So what was now the last one from last week? I think we were still busy with MinPad 1, because that is MinPad 2. Yeah, that figure we had, this one, that is the low quartz, we had the trinamite, we had cristobalite, we had low quartz, high quartz, we had. Yes, now let us just continue with this figure. I mean, I showed you last week this figure as well, but just to repeat some things. Yeah? So I mean, I introduced last week the entropy and the enthalpy. Yeah? So if we are looking at this phase diagram of quartz, I mean quartz is also a polymorph mineral. You know by now what polymorph minerals are. For example, the alunosilicates, these are polymorph minerals. And the quartz is a polymorph mineral, and then the titanium oxides, the rutile, the anatase, and the bruchite is a polymorph mineral. And then you know some other polymorph minerals by now, like the serpentines, yeah? So when these polymorph minerals are called polymorph minerals because they have always the same chemical formula or the same mineral chemical formula, yes, to be scientifically correct. So, and here we have this one from the quartz, and here we have the low quartz, yeah, and Neil showed you, or I showed you last week, the typical low quartz, that is this one, yeah, it is a hexagonal quartz, and you can see very nicely the shape, yeah, and we will do in the common weeks a little bit crystallography as well. There I will then introduce you into the different crystal classes and the different symmetry operations. So, but here now we have this quartz here, that is the low quartz, has a density of 2.65, yeah? Then we are increasing the pressure. That means we are making then from our low quartz, we are making a coesite, and the coesite has a higher density because while we are increasing the pressure, we are decreasing the volume of every cell unit, and therefore at a given mass, and therefore the density will increase. Whereas if we are heating up our low quartz, then the density will decrease because the volume will increase and the entropy will then also increase. Yes, I introduced last week the entropy, and that is that shows you the entropy shows you the disorder of a mineral or a phase. Yes. So the easiest thing to see this or observe this, that is if you are looking at water, yeah. Because if you are boiling water, then the density will decrease and the volume will dramatically increase because you are producing the steam out of your liquid water. So and therefore the entropy will then increase because the water becomes, or the molecules in the water molecules becomes then more disordered. So, and that is for every other mineral on this planet and on the outermost space and the inner space and the galaxies, everywhere the same. So, and then I introduce the enthalpy, and that is how much heat a phase or a mineral can store. Yeah, I gave you last week this example using iron and porcelain. So when the iron can store much more heat compared to the porcelain. So and now we have then to increase, also introduce the chips-free energy, and that will be then later today. So now next slide. So I showed you all these different crystal structures, and here we have the structure from a forsterite, and the forsterite is a nesosilicate, yeah? The forsterite is a nesosilicate, and the garnet is a nesosilicate, and we have some other common nesosilicates. So when I wrote down the exchange vectors from the olivines, yeah, there you have the Fm exchange, the forsterite is the Mg2SiO4, whereas the other very famous end member is the firelite with Fe2SiO4. Yeah, you have written down this in your booklets. Yeah, we have done this a couple of weeks ago. So and then the garnet, we have also written down, or you have written down the structural formulas of the most important 4 end members of the garnet. Yeah, the pyrope, the almandine, the grossular, and the spessartine. Yes, we have. Can you just check it? That is the one with the 12 oxygen. Yes, you have it, or? Yeah, that is the tile, yeah, that is before we have done this, the gypsum, the borates, yeah, you are writing here everything. Here it is. There we have the 12 oxygen. Yes. Here we have the almandine, the pyrope, and the grossular. And you have forgotten to write down the spessartine. Yeah? So that should be good as a homework. Yeah? So, but anyway, we have here the forsterite structure, and we have here different levels. I mean, the big blue bubbles, these are the oxygens, because oxygen is a big bubble. And you have always between the oxygens, you have the tetrahedrons, and inside the tetrahedrons you have the silica. So, and then we have here on certain levels, we have the magnesium or the iron, yeah? So, and if you are checking this nesosilicates, then you can see that the tetrahedrons not connected with each other, yeah? They are always single tetrahedrons, yeah? So, but if you are going back into your documents just to last week, you can see, or if you are comparing the structure, the crystallographic structure, with the tectosilicate, and the tectosilicate is the quartz, then all the tetrahedrons are connected with each other. Why is this so important? An olivine, for example, that is always in undersilicated rocks, that means we have a lower silica, the silica concentration is lower than 50% or 48%, and that shows, or that means that you have the low quartz inside, because I told you before, quartz and olivine are never occur together in a rock, especially in some very special varieties, but then they are not in equilibrium. So, and if you have an ultramafic to mafic melt with a lot of olivine, then such a melt has a much lower viscosity. So, and that is very important because a melt having a lower viscosity is the more liquid, and such a melt will flow down the hill faster. So whereas if you have a silica saturated melt, silica saturated, and the other one is a silica undersaturated, and when you have a silica saturated melt, that means your tetrahedrons are all connected with each other, and therefore such a melt is not that mobile, and therefore the viscosity of such a melt is higher, so and therefore this melt is not that mobile. So that it's very important for those of you doing next semester the ES201 and the ES203, because there we will talk much more in detail about the different types of melt. So that is now such an nesosilicate, yeah? And for you as an ES203 student, it is important that these nesosilicates, that the tetrahedrons are not connected to each other. So, and then we have here M1 spaces and M2 spaces. I told you this as well before. An M1 space, that is an octaeder space, and the M2 space is an octaeder space. And these are the spaces where your metals are sitting. Yeah? The magnesium, the iron, the calcium, the manganese, and blah, blah, blah. So, but anyway, the M1 space is smaller, whereas the M2 space is bigger. So we have written down a couple of weeks ago also the pyroxenes. Did we, or can you just check it if you have written down the pyroxenes as well? That is with the 6 oxygen. The 6 oxygen. Where do we have the 6 oxygen? Should be also somewhere here. Then we have the CO2. Here we have the double chain silicates. Yes. So here we have ultra-wet basalts, blue schists. I think we have done it before. There we have the olivines, the feldspathites, the plagioclases, the pyroxenes, that is 06. This one, that you have to do as homework. So the pyroxenes we have, but I think we have made them, but anyway, then I will just do it again. The pyroxenes has this 06, every pyroxene has 6 oxygen. So then we are making now the pyroxenes. So, and therefore we have the autopyroxenes. So why they are called autopyroxenes? Because they are autorhombic. So and now this semester I cannot show you an autorhombic crystal because we have just ordered wooden crystal models. So but for those of you failing the class and making it 1 year later, then I can show you the autopyroxene in a wooden model, and such an autopyroxene, I can just draw it here. Oh, it looks not like this. So So, and then you have the angle alpha, beta, and gamma, and they are all 90 degrees. Yeah? Alpha is beta, is gamma, and they are all 90 degrees. So, but the lengths here, A and B, has the same length, but C is different. Yeah? So that means A is B, but C is different. Yeah, that's an orthorhombic crystal. Yeah. So and therefore we have the two orthopyroxenes. One end member is the N-statite. It's M. And so and therefore I'm making now the M spaces. We have an M2. We have an M1. We have the tetrahedron spaces, and then we have the oxygen. Then I told you every pyroxene has 6 oxygen. Oh, 6. So, but the N-statite and the ferrocylite, you can also divide it. Then you have 2 silica, and here you have a magnesium, and here you have a magnesium. Yeah, that is the Mg2Si2O6, but you can write down the formula also MgSiO3. So then we are making a ferrocylite out of it. So that means we are making the Fn exchange. Fn, you know by now, that is iron, magnesium. Then you have iron, Si2O6. Yeah. So then we have here the clinopyroxenes. So there we have the more, we have the dioxide, we have the Hedenbergite, so then we have the jadate, and we have the acmit. So, and these clinopyroxenes, they are called clinopyroxenes because they are monocline. So, the crystal, the shape of the crystal is different, which we will do then. How many weeks do we have till the midterm break? 2 weeks. Okay, that we will then make it 2 weeks. I mean, we have the next week class and the following week class, and then it's midterm break. Yes, okay. So then we have this there. I will show you then the different crystals. So then we have here again the 2 silica, the 6 oxygen, but here we have magnesium on the M1 side, and here we are putting something inside, which is then bigger because the M2 space is bigger compared to the M1 space. So in which element do you think we can put in then there? There we are putting a calcium. So, because calcium, if you are going through the periodic table, the calcium atom is bigger compared to magnesium. Then we are making with these 2 guys again an Fn exchange. You should be easily able to do this by yourself with calcium, iron, Si2O6. Yep, finish. So then we have the jadate. So and now we're at the jadate, we are putting here another atom. So and there we are putting the aluminium. So and the aluminium has 3 electrons in the outermost rim. That means we need here in front a big atom which has only 1 electron in the outermost rim. So in which one could this be? That is the sodium. So in such a chardite is a mineral or a pyroxene which is stable at very high pressures, yeah? Such a chardite you can find actually in blue schists, yeah? So then we are making the agnit. We have here also a sodium. Here we have Si2O6. So in which element we has also 3 electrons and is nearly of the same size as or like aluminium. A common element, yeah? I mean, there are a lot of other pyroxenes on this planet. I told you, we have by now discovered 3,000 minerals, but you should only have the most common one in your head. But if you like to visit a place where you can find all 3,000 minerals, then you have to go to South Greenland, to the Mausak intrusion. There you can find all the 3,000. And I was there, and it is true. Or you can go to Murmansk in Russia. There you have also such an intrusion, and there you have also nearly all the minerals which you can find. And in Murmansk, there you can find something else. You can find a wrecking stage for the old nuclear power submarines used by the Russians. And afterwards, you don't need a torch while you are going through the light because you are shining by yourself. So, but anyway, this other element here, that is iron 3+. So, and now we have the pyroxenes, yeah? So, and that is the thing with the N1 and the N2 spaces, and I gave you a couple of weeks ago an example for the N1 and N2 spaces using the sheet silicates, yeah? So, in there I'm very sure that we have done this. So, and now we are going to the next slide. So here we have just another view from such a forsterite. We must not go through all these things. I mean, for those who are interested in, you can go just to the internet in Google. There are from some universities some programs uploaded, and then you can just construct these things by yourself and turning it around and blah blah blah. Yeah. Next slide. So that is then another forsterite structure from another point of view. Yep. So now we are going back to the mantle, yeah? So, and here we have now a cross-section through the mantle, and this cross-section is actually representative for areas like we find it here in Fiji, yeah? Or in the whole Pacific. So, because at the top we have the oceanic crust, yeah? So, in the oceanic crust contains or consists of minerals. I mean the gabbro, yeah? The plutonic rock from the oceanic crust is a gabbro, and you have seen these gabbros in the Yamuna Creek, or they have been in Yamuna Creek at the ES203. No, you know, that's also a pity. It is a pity. So, because there one would have seen the gabbros. So, that is it's really a pity. So, but anyway, there are gabbros. Do we have a gabbro here as a hand space event? Yes, we have gabbros here, of course. So, in this oceanic crust is an average 7 kilometers thick. And contains of basalts at the top, because the basalts have cooled down much faster because they were in contact with the water. You have these pillow basalts, and you have seen the pillow gabbros. Yeah, here we have a nice gabbro, yeah, that is a nice one. And here it is a polished surface, and there you can see some black crystals inside, yeah. And these black crystals, these are then the pyroxenes from the gabbro here, from the oceanic crust. And then you can see some white minerals inside, and these are the plagioclases, yeah? And these plagioclase, which you can find in the oceanic crust, these are anortites, yeah? So in the anortite, that is a calcium-rich plagioclase, and we have written down the formulas from the plagioclases. Just check it, that is the one with the 8 oxygen, yeah? So then with these, we have the lithosphere here, and the lithosphere can be subdivided, or the lithosphere, that is our conductive mantle, and the lithosphere has an upper part, and this upper part of the lithosphere are made up of rocks which we are calling Harzburgites. So, and I gave you a few weeks ago the triangle of the Harzburg, of the peridotites, and there's also the Harzburgite inside, and the Harzburgite consists mainly of olivine and autopyroxene. So we have about 80% of olivine and 20% of autopyroxenes. So below the lithosphere here, below the Harzburgite, you have a layer which is made up of lersolites. So in these lersolites, they can contain additionally a third important mineral. They can contain a plagioclase, that is called the plagioclase lersolite, or they can contain a spinel, that is the spinel lersolite, or they can contain the garnet, and then there is a garnet lersolite, yeah? Well, just go back, yeah. So that is then the lithosphere, that is the oceanic lithosphere. Yeah, and I have drawn you a lot of times such a dipping slab beneath the continental crust, and that is how the whole package from the oceanic lithosphere is made up. And of course at the top here you have then the sediments, yeah? So then here we have the boundary between lithosphere and asthenosphere. So in the asthenosphere, that is the convective mantle. That is the convective mantle. And the convective mantle is then made up of a pyrolite, yeah? So in this pyrolite, that is a model chemical composition of a rock, because nobody can go there, nobody can drill there. So, and then Ringwood in 1967 introduced the pyrolite. So, but the pyrolite is more or less of lersolithic composition. So, and then we have, that is then the upper mantle, yeah? So, and at the bottom here between, we have then here in 400 kilometer geophysical boundary or seismic boundary, that is the D layer. And then in the depth of 600 kilometer, we are running from the upper mantle into the lower mantle. Here in the upper mantle we have pyroxenite, beta-spinel and schistosite. Schistosite, that is this very high dense quartz variety. So and here in the lower mantle we have then the gamma spinel. The gamma spinel is just a more close package from the bolts, from the atoms, compared to the beta spinel, because the beta spinel is formed at lower pressures. So and then we have here the perovskite and the periclase, and you know by now the periclase as well. That is the MgO, which we are using for the ternary system, for the NSH system. So next slide, please. So that is, I don't know what this is. Not important. Next slide. Yeah, that is our perovskite. That is the closest baggage. So when this perovskite is then stable under very high pressures, in the lower metal, and therefore you have to have the closest baggage because of the high pressure. So, next slide. So here we have the spinel, and the spinel, they have, all spinel have this geometry, and that is also a very close baggage. So because the spinel, I told you before in this slide, from the beta spinel and the gamma spinel, and if you are having a spinel which is formed at higher pressures, and that is now for you important, that as an ES203 student, then the baggage becomes then just smaller. So, but that you should have by now here inside, because I'm telling this now a lot of times. That means what you should have in mind: you are increasing the pressure, then you are decreasing the volume, and you are increasing the density. That's all. Yeah. Next slide. So then we have here the perovskite again. So then we have the perovskite that has a big calcium inside, yeah. That is this bubble, yeah. So and then we have 6 times coordinated titanium. So and these are in the M spaces, and surround we have the oxygen. So and this perovskite is also a very close package because the perovskite is formed under very high pressures. So next slide. Yes. So I mean, if you are looking at hexagonal baggage layer, then we have this arrangement of our bubbles. Then we are, that is the one layer, the A layer is the blue one, and then we are putting here then inside the B layer. So and then we are putting here inside the C layer, and then we are putting inside the C layer, that means another bubble on the top. Then we are running from the hexagonal baguette into a cubic baguette. So and the cubic is the most close baggage what you can have. So that means under very high pressures you will not find any hexagonal minerals because they are running then into the cubic system. So, what you should have then in mind as an ES203 student, you are changing just the arrangement from your bubbles while you are increasing the pressure so that you can increase the density. Next slide. Yes, that is the same story again. We have here our hexagonal system, 1, 2, 3, 4, 5, 6, yeah, that is hexagonal. I mean, you must just watch this quartz again, and then you can just see how it works. That is hexagonal, yeah. So, and if you are putting the quartz like here, then we have again hexagonal, yeah. So, and if we are now running, if you are increasing the pressure, and we are putting a lot of pressure on our hexagonal symmetry, then we are producing here this one, and if you are following the red lines, then it is not longer a hexagonal crystal, then we are making out of our hexagonal crystal a cubic crystal, yeah? So next slide. Yeah, these are now the Miller's indices. The Miller's indices that works like following. We are just, but we will do this more in detail in 2 weeks. But the Miller's indices are just used to describe crystals. So I mean, we have here an axis coming out, here an axis coming out, here an axis, here does the axis coming out, yeah? Here, so that's the way how it is scientifically correct. So then this is here we are using the Miller-Schick index 100 because the X is just coming out here through this plane here. So, and that is then C that goes out here, that is 0, 0, 1. So, and then it is, this one is B, and that is 0, 1, 0. So, because that is A, B, C, so, and that is B axis, and only B comes out here, that we have here to write a 1. So, that is the A axis here. A just crosses out here in the middle of the plane, therefore we have here a 1. There's nothing coming out in the direction of C, nothing coming in B, nothing coming out in the direction of C, and here nothing coming out in the direction of B. So therefore we have here just the 1. The same for here, nothing is coming out here along this axis, so then we have here 0, here 1 comes out here directly, then that is 1, and here we have again 0, because nothing is coming out here. So, but that we will do more in detail then, when I have their prepared class. So, but if we are running out here at the corner, then we have 1, 1, 1, yeah? So if we are running out here, that is then 1, 0, 0. If we are running out here, that is again the 0, 0, 1. If you are running around here, that is again the 0, 1, 0. But here we are running around this corner, yeah? Then we are going one time in this direction, one time in this direction, and one time in this direction. So if we are doing this on the negative side, for example here, then we have 1, 1, minus 1, because we are running then around there. So just keep this in mind when and we will discuss this later on when I have the movies. So next slide. So what is this now? That is the pyroxene structure, yeah? So that is the structure from these guys I have written here, yeah? So and that looks quite complicated, but it is not complicated. So what is then the blue bubble here? I mean, we have a big bubble here. So, and you know, here in the tetrahedron, inside the tetrahedron, we have the silica. And at the corner of the tetrahedron, we have the oxygen. So, and if you are looking at this guy, which of these pyroxenes could represent this model? We have bubbles here of two sizes, a bigger one and a smaller one. So the bigger one could then be the calcium, or it could be the sodium, and the smaller one the magnesium or the iron or the aluminium or iron 3+, yeah? Because here the calcium or the sodium is bigger than the magnesium, therefore we have here bigger bubbles. So if we would have such a plot from an autopyroxene, then all the red and the blue bubbles would be on the same size, yeah? Because here these guys are of the same size. So next slide. So here, for example, we have just a pyroxene from another point of view, yeah? But here you have still such a kleiner pyroxene, the red bubble and the blue bubble. So next slide. So that is now a wollastonite, yeah? So in the wollastonite, that is if you are drawing the pyroxene triangle, yeah? So then we have here the enstatite, yeah, that is this guy. Then you have here the ferrosilite, that is this guy. Then you are making here along this axis the Fm exchange. So then here in the middle here, you have here the dioxide. And here you have the Hedenbergite. And here at the top you have the wollastonite. And the wollastonite, that is a calcium 2 Si2O6. So in there the bubbles have now all the same size. So that is now the same structure as you will find, or like you can observe in the autopyroxene, like in the enstatite and in the ferrosilite. So next slide. That is the wollastonite from another point of view. Next slide. So that is how the pyroxenes changing their crystallographic symmetry while we are increasing the pressure and the temperature. So here, for example, we have at very high pressures but lower temperatures, lower than 600 to 700 degrees, we have a clinoenstatite. So while we are increasing the temperature, we are having the autoenstatite. So and here at very low pressures we have the protoenstatite. At temperatures higher than 1600 degrees Celsius or something like this, we are forming the liquid. So that means our enstatite is then molten. So and that is now, while we are increasing mainly the temperature, then we are increasing the entropy, we are increasing the volume, and then your bubbles swirling more and more around in a bigger space, yeah, as you are like, in the same way like you are increasing the temperature while you are making from water steam. So, next slide. So that is just a phase diagram between olivine here, Mg2SiO4. Here we have the enstatite, that is then here, and here we have SiO2. I told you quartz and forsterite, they never occur together. So then we can have either a rock containing forsterite and enstatite, that is a harzburgite, or we can have a rock which contains quartz and enstatite. So while we are increasing the temperature, our phase relationships are changing. Here, for example, we have a peritecticum. At the peritectic point, there we have incongruent melting. So that we will discuss more in detail in the ES203. So there we have incongruent melting, and that means we have forsterite plus silica, we are making then here an enstatite. So and here we have the eutecticum, and there we have congruent melting. That means we have a enstatite and we are just making from this enstatite melt. So and here we have then a thermal boundary. A thermal boundary means you have your melt coming down to this point, then your melt can crystallize on this side, Forsterite plus Enstar type, or you are running down here the hill, then you are crystallizing then Enstar type plus quartz. And because of the thermal boundary, Forsterite and quartz cannot thermodynamically not occur together. So next slide. Yes, here we have the high temperature phase relationships in the binary Mg2 SiO2 system at 1 bar, that is then at atmospheric pressures. Here we have 100% MgO, here we have 100% SiO2, here between we have the Forsterite, here we have the Enstar type. So here, for example, we have periclase plus liquid. Here we have only liquid, that means melt. So then we are coming here, if we are coming down here and cooling down our melt, then you can go on the thermal boundary to this direction, or you can go down to this direction. If we are cooling it down here along this curve, then we are coming here to this eutecticum. So here we have again the peritecticum, which is for incongruent melting, and here we have again the eutecticum. So within these phase relationships, you can form, or you will have different minerals. So here, for example, in this field, you have the Forsterite plus the periclase. Here in this field, you have cristobalite, that is a quartz with plus liquid. So it depends always on your original composition of your melt. So in the original composition of a melt, that is the given thing, yeah? So if you have at the beginning a melt which contains a lot of quartz or silica, then you will crystallize at the end the quartz, yeah? That is of course so. So whereas if you have a melt, which contains from the beginning more MgO and less silica, then you will form different minerals, of course, yeah? So I think that is then for Wednesday a good exercise. Just give them all these diagrams and then they should draw in the cooling passes. You have the 303 documents, and there I have drawn in the cooling passes. So they should do this on Wednesday, and then they should do on Wednesday as the same with these binary diagrams, you know, these banana diagrams with the plagioclases and the olivine, and the drawing in the cooling passes. Because that is a thing one have to do by exercises, because it is actually a totally simple thing, but you have to do it one time by yourself. So, and I cannot draw here on the board, because otherwise they will charge it for my salary. So, next slide. So here we have the different composition, varieties of the composition in the MSH diagram. You know this by now, in the MSH system, yeah, where you have the MgO, the silica, and the water. So, and I showed you the MSH diagram by using the different mineral composition inside, and you have written down last week the mineral reactions, yeah. So, and there we have the different, we are running here on 15 kilobars and 1280 degrees Celsius. So, and then if we have a melt which contains a lot of magnesium and water inside, then we are forming Forsterite plus vapor. So, because for the Forsterite, we need 2 magnesium, yeah? Whereas if you are running on this side, we have much more, we have then on this point no magnesium inside, so then we have here just liquid that is smelt. Here we have then the enstatite and the liquid, yeah? So you can see from this diagram again, here you have our Harzburgites in this field, whereas here you have the enstatite plotting. So and then you have a field where you have enstatite plus liquid and vapor, or then later on the quartz. So but from these phase relationships you can easily see that the quartz and the olivine can never occur together in a rock. Yeah? So and then it could be, for example, a question for the test. So, and I think for test number 1, I will just upload on Google the test number 1, yeah? So, and then you can fill out in the homework your test number 1 and then hand it in class in the first week after the midterm break, yeah? So, and I will upload it on Moodle. Sometimes, I mean, I'm in Paris next week, but maybe we can do it while I'm sitting somewhere at the airport, yeah? So, and I mean, these tests that are a little bit more difficult than a test which you have to write in here in class. Therefore, I'm giving the tests as a homework. So, and then you have to study the whole thing, yeah? You have to study it very hard. And then we are doing a second test by the end of the year, something like this, yeah? You have then also 2 weeks time. And if you are studying for the preparation for the examination, these 2 test papers very carefully, then we should make the examination actually very easy, yeah? But you have to make these tests. So, and there I will have then also some question maybe regarding the phase relationships between the olivine and the quartz, yeah? Next slide. So that is now a beryl. We will not talk anymore about the beryl because the beryl is actually not that common mineral. I mean, the beryl is very important if you are looking for a beryllium ore deposit, yeah? And at the beginning of the class, when we discussed what was it? Very at the beginning of the class, when I showed you the first figures, there was one figure, one picture of a beryl, and I mean the beryl is a ring silicate, and here you can see again these rings, yeah? So, and this is hexagonal. So, and that is, I mean, I told you this also at the beginning of the class, how the symmetry of a mineral which you can observe in the field, like here the quartz, yeah, reflects on the atomic structure. That is the nice thing in mineralogy and petrology, that everything fits together. Yeah? So next slide. So what is this? That is just a beryl at another plane. Yeah, next slide. Finish. So then we are going to our next presentation. That is then the petrology or MIPET 2. So what is this now? So that is now again the MSH triangle. I mean, you know it by now. And if you are running from here to here, then we are adding water. If you are running from here to here, then we are adding magnesium. If you are running from here to here, then we are adding silica. And you have used this triangle last week as well, is it or not? To write down the reactions. Yeah, you know this by now, lucky, yeah? Yesterday, yeah. So then you should still remember it. So next slide. So now what is this? You should by now also be able what this is. Yeah, I mean it is a silicate because we have here the tetrahedrons, yeah. So, but what for a silicate is this? And what for a silicate is this, yeah? And what mineral is this? No. This one is a pyroxene, yeah, that I can see from here. But this one is not a pyroxene. That's just the other, the second presentation. We did by now one mineral group with an interlayer. So which one was this? The interlayer, and we have written down all the formulas. That is talc, yeah. So that is great. That is great. So to which mineral, to which silicate group the talc belongs? Sheet silicates, yeah? Yes, that is great. Sorry. So that is a sheet silicate, and that is the talc. So, and you know that sheet silicates have an OH2 group, it's a hydrous mineral, and here this very light colored blue bubbles, this is then the OH2 group, yeah? So then you have here the tetrahedrons. The silica is sitting inside the tetrahedrons, and at the corners of the tetrahedrons there is the oxygen, yeah? So that would also be a good question for the examination. I'm just printing out such a picture, and then you can tell me during the examination which element is sitting where. So, and these red ones, that is then the magnesium, that's all, yeah? And the interlayer is empty. So next slide. So what is this now? And that was the TOT structure, yeah? We have written down this, I saw it just in your notebook, yeah? So, and what is this now? That is also a sheet silicate, showing also a TOT structure, yeah? So, but here we have something in the interlayer. What? No, that's not a biotite, that is a fluoride. That is a biotite, and this biotite could be a fluoride or an amide, yeah? So, and therefore we have these bubbles here inside in the interlayer. So, and now you should be able to tell me what are the pinkish bubbles are in the interlayer. No, the magnesium is the red one. That is what? No, the silica is sitting inside the tetrahedron. That is the potassium. That is the potassium because the potassium is a big bubble, so the potassium is here in the interlayer. So and if you are looking here at the biotite crystal, here we have some biotites. I mean that is a sheet silicate, yeah? And you know by now why they are called sheet silicates, because they are forming these different layers of sheets. So and I mean you can easily remove one sheet from the other one, yeah? So and then while you are squeezing or pulling these sheets apart from each other, then you will lose the potassium. So next slide. Oh, that was the next slide. We had this already. So that is now, what is this now? That is a TO structure, yeah? So in such a TO structure, that is, for example, a kaolinite or something like this, yeah? That is not that important because you have a lot of OH inside. You have twice more OH compared to the biotite and the type structure before. And that is in reality as well that the kaolinite contains OH4 while the talc and the biotite contains OH2. So next slide. So what is this now? We have a TOT structure, but we have more water inside. We have here, even in the interlayer, a lot of light blue bubbles inside, and that is a chloride. Yes? Yes, that's a chloride. So if you are checking in your documents the chemical formula of the chloride, then you can see that the chloride has much more OH inside compared to the biotites or the talc. Yeah? So next slide. So here we have, for example, the talc structure. That is TOT. Yeah? Here we have the brucite. That is just the brucite. That is just NgOH2. So then we have here the antigorite. The antigorite has just the TO structure. So and then we have the mica structure with the calcium, with the potassium or the sodium or even calcium in the interlayer, and that is the TOT interlayer TOT structure. So next slide. So that is now phase relationships in the MSH system. We have here again N-statite, we have quartz, we have talc, we have Weber. So in the talc, that is an OH-bearing mineral. Here we have an OH2 group. So therefore the talc is plotting more on this side. So and therefore, if such a talc is dehydrating, then you will always get from hydrous minerals such a bend. Yeah, that from here to here, we are dehydrating such a talc. That means the talc will release its OH2 group, and then you will produce from your talc an N-statite. Yeah? So when this dehydration can happen, I mean here we have just a solid-solid reaction and a solid-solid reaction that is just a water-free reaction. It is just diffusion controlled. So whereas when we have these bends, then we have a dehydration reaction. So a dehydration can occur by heating, dehydration can occur by compressing, and dehydration can occur by decompressing. So if we are writing down this reaction, then you are putting the hand on the tile, and then you will form, enstatite plus quartz plus vapor. So, but that you know by now from the exercises yesterday, yeah? So, next slide. So, now we have here the phase relationship. Forsterite, enstatite, quartz, talc, vapor. So, and now you can use this also, this example, for training your the writing down of your reaction. So if we are putting here the hand on, then we have the Forsterite missing reaction. So and then we have the reaction talc is enstatite plus quartz plus vapor. That is here. That is a stable reaction. We are talking in petrology always about unstable, metastable, and unstable, metastable, and stable. So, and therefore one can have an easygoing picture to understand it or not. So that is actually the thing here. So and here we are making, we have the Forsterite absent reaction. Then we are making, then the talc will dehydrate and form 3 enstatite quartz plus water. So and that is a stable reaction. So, and if we are talking in thermodynamics about stable relationships, then what do you think? We are making 3 balls here. That is 1 ball. That is the 2nd ball. And that is the 3rd ball. So, and which of the balls do you think is in a stable relationship or stable condition? That is this one. That is stable. So because if the ball is here, then it's just lying here, and then it's stable, nothing else will happen to it. So then we have this relationship, the enstatite missing relation. Then we have here a reaction which is talc will give you enstatite plus quartz plus vapor. So, and that is the metastable. That is the metastable relationship, yeah? So, and what is indeed, and if something is metastable, then you need just a little bit energy to run the reaction, yeah? That means if you are talking about in a petrological or mineralogical relationship, then we have just to change the pressure and the temperature condition, yeah? So, and then we have a meta, and then the reaction will go on, yeah? So these minerals, if we are talking about minerals, then these minerals are stable, but if we are increasing the pressure and the temperature, then another reaction is going on. So in which of the 3 balls is the metastable? You need just energy to kick out the ball. Yes, that is the middle one. So because we can just force it, and then the ball will run in here going down, and it becomes metal. And here it is metastable, and here we are stable. So for example, everybody of us is metastable, yeah? Because you are getting bursts, and then you are getting older and older and older, and you are changing actually from day to day your shape, yeah? And your cells will decay and so on. That is the metastable. Stable is then when we are just dying. Then we are in a stable. No, we are actually also not in a stable condition, but very soon. So, and then we have now, that is not written here, we have unstable, and that is this one. So there you don't need any energy. The ball can run down here, or the ball can run down here, yeah? You cannot keep it, yeah? So, and these are then the few things: unstable, metastable, stable. So, and there you can write down this different mineral reaction with our hand method. So, next slide. So then we have defect structures in crystals, because a natural crystal is not perfect. So there are always defect structures inside. So, and I mean that we have on the first place, we have a perfect crystal, so every atom is sitting on its place, yeah? So, for example, if you are going, or if you, some of yours maybe, I don't know if you have been preaching these possibilities, but maybe some of yours will go into the industry, yeah? And in the chemical industry or in the material science industry, yeah? With this stuff we are hanging in the material science industry. So when they are in material science, they are making the crystals by themselves. So in the most famous crystals, what they are making by themselves, these are the wafers, you know, the chips. So, and I mean they are making the huge crystals by themselves, you know, they are this diameter and this high, yeah? So, and these are this, these are perfect crystals, yeah? So, and then they are making the chips out of it, or the wafers. Everybody has these wafers in the cell phone, yeah? And then they can, then they make defect structures inside, yeah? They make it by purpose inside, so that they can program the wafer. So, but natural crystals are never free of defects, yeah? And every natural crystal has some defects inside, and there you can then put some other atoms inside, or for example, OH, yeah? So I mean, I told you just, I don't know when I have told you, but sometimes I told you this, that you have in the Earth's mantle a lot of water, but you do not have hydrous minerals in the Earth's mantle. So, and then this water must somewhere be, and that is then just sitting on defects, yeah? For example, here number B, we have the Frankel defect, yeah? So, in the Frankel defect, I don't know why it is called Frankel defect, but maybe the scientists who discovered the Frankel defect, his surname was maybe Frankel. But I'm not sure, and therefore this is not a question in the examination. Who was Frankel? So, but anyway, there atom is missing, yeah? So, and then you can put in such a defect another atom, yeah? So, and that is in nature, it can be everything, yeah? It can be the whole periodic table, and the most famous one nowadays, that is hydrogen, or OH, yeah? So in the industry, they are making then these defect structures by themselves in a certain order, and then they can dot other elements inside, and then that's the way how they are making the chips. And with this stuff, you can make a lot of money. But then you have to go maybe, I don't know, Silicon Valley or so. There they are making chips, I think. So then we have the Schottky effect. Here the atom is missing and then it's just somewhere inside, somewhere else. So and then we have the impurity defect, the interstitial defect. There you have a perfect crystal, but another atom is just somewhere sitting inside. So and these defect structures are called point defects. Yeah? Point defects. And if I remember my course outline very well, then we should come next to the planar defects. Yes. So we have the linear and planar structural defects. So here we have the screw location. So and therefore we have just added another layer here, and then you have a lot of space to put another element inside, or another elements. So or you have the planar defect like the next one, then a whole layer is missing. So and that is actually acting like a grain boundary, yeah? So and if you are going back to these pictures, how it is to our metal structure picture, I mean we must not go back now, but then you know at a certain depth and you have a high temperature and high pressures. So and I mean there you have not grain boundaries, yeah? There you do not have grain boundaries. The whole thing there it is more or less like a dove, yeah? Like a dove. So and therefore these planar defect structures or monomineralic grain boundaries, they are just walking or moving through a crystal, yeah? So and if this rock is then cooling down, then you are getting all these grain boundaries and these planar defect structures and blah 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 as frozen remnants from your originally dove. So or you have these lineage structures, so there is then a network here of planar defect structures. So and that is then how it looks like later on, how it forms then later on the grain boundary. And there are some nice experiments done. I mean they make these experiments in the industry, and there are a lot of movies around in the internet. You can just check it in the internet by just googling it, dislocation creep. Yeah, you can show them next week the dislocation creep. Just put in Google dislocation creep, and then you get all these videos. So and then they have done it, you know, under the microscope, and then you can see how the grain boundary is moving in a crystal. So and that's the way how the water becomes pumped through the Earth's mantle, yeah, that is the dislocation creep. And these are just these defect structures. Next slide. So what is this now? That is now again M2, M1, SIT1, SIT2. That is then again, what is this? That is a pyroxene. So next slide. Yes. Here we have it, I'm saying it, and then we have it here. Here we have again the M1 space, that is the smaller one, and the M2 space, that is the bigger one, and the tetrahedrons between. Next slide. So, and what is this now? This is now an amphibole. So we have not discussed one mineral group, and these are the amphiboles. The mineral chemistry of the amphiboles. So, that is then also something for next week. If you can just give them a copy from this page and from this. So, because there are all the silicates, yeah. So, and here is the amphibole group. And here is the amphibole structure. You have the A place, that is the interlayer. You have the 2 and 4 places, 1 and 2 place, 1 and 3. Yes, and 1 and 1, 1 and 2, 1 and 3. Then you have 7 octaeder spaces. Here you have the 8 tetrahedrons and the OH22. And then they should just fill in this in the formulas, into this structure. You know what I mean? Okay, great. Just these 2 pages. So, and then you can, that is then the second part of the exercise, yeah? Then you can do with them on Wednesday, what? The banana and the smell diagrams, and then on Thursday they should do this and writing down all these things. So, and they should then also write down again all the formulas what they have given to us or what I have given them, yeah, together with the amphiboles, fill it in, yeah, the bigger bubbles in front, the smaller bubbles in the back, and blah blah blah, and then we will collect it. Yep. Okay. So next slide, that was now an amphibole. So what is this now? Here we have a bigger bubble, we have the tetrahedrons and the tetrahedrons all connected to each other, but we have an additional bubble inside, so that is the northern parts. But what other very famous tectosilicates do we have? The K-felds, the feldspars, yeah, that is the plagioclase, and the plagioclase can be subdivided in anortite and albite, and then you have the, what is the other guy called? The K-feldspar. So next slide. So that is just another plagioclase or the plagioclase from another perspective, yeah? And you can see very well that every tetrahedron is connected with another tetrahedron, and therefore they are called tectosilicates. Next slide. So that is just a plagioclase from another perspective. This as well, yeah, next slide. So then we have here, we can subdivide the tetrahedron spaces in T1 and then the T2. That is just the direction in which the top of the tetrahedron is looking. So next slide. So that is again the feldspar structure, yeah. Next slide. So yes, and I mean, of course, here we have the distribution of aluminium on the tetrahedron side in the feldspars, and then the position of the aluminium or the distribution of the aluminium over the T1 and the T2 space varies with the temperature. So, and then while we are increasing the temperature, then the volume will increase from your feldspar or from your plagioclase. The density will decrease, the volume will increase, and the entropy will also increase as well. And you are changing the crystallography from your mineral, and therefore the arrangement of the tetrahedrons. That's all. Next slide. So here this diagram you know by now. That is the triangle of the alkali feldspars. We have here the anortite, we have the albite, we have the autoclase. Here we have an invisible region. That means the composition here inside is not stable on our planet and on the other planets as well. The albites can be subdivided here if it is a calcium pure, the plagioclases can be subdivided. If it is a calcium pure plagioclase, we are talking about an anortite. If it is a sodium rich plagioclase, we are talking about an albite. So in between these two end members, as we are calling it, we have then the albite, oligoclase, andesine, labradorite, butonite, and anortite. Whereas here we have the alkali feldspars, we have the sanidine, the sodium sanidine, and the anortoclase. So at a temperature of 800 degrees Celsius, we have a visibility gap here. We have here the sodium autoclase, here the plagioclases, but here we have this visibility gap. So and there you are forming the peartides or the antipeartide. And I told you a few weeks ago what a peartide is, and I told you as well what an anortite is, what an antipeartide is. So the other one have exsolution lamelles from K-feldspar in the plagioclase, and the other one the other way around. So next slide. So and here we have the same situation using different curves So at 900 degrees Celsius we can have an alkali feldspar with this composition, yeah. At 750 degrees Celsius as well, whereas at 650 degrees Celsius we have there again. So that means at 650 degrees Celsius we cannot form an alkali feldspar with this composition, yeah? Not possible. So next slide. So that is then the next diagram also for Wednesday. So but that is now not in the forsterite quartz system. Here we have just here the K-feldspar, and here we have the calcite or leucite, and here we have quartz. So here we have the same situation as for the olivine and quartz system. You can have not a fluid, these are fluid minerals, yeah, the calcite, the leucite and the nephelinite. And these fluid minerals, if you are going very back to the beginning from this class, I gave you the QAPF diagrams, where we have on the lower side, we have the fluid minerals, the silica undersaturated rocks, whereas at the top we have the triangle for the silica saturated rocks. That means quartz cannot coexist here with fluid. Here, for example, we have again the peritecticum, and here we have the eutecticum, and here the different phase fields. So, and then he will just give you next week a few composition, maybe one composition here, one here, and then you can just draw in the crystallization of these rocks and minerals. So, next slide. Yes, that is how it works. The pressure dependence of the phase relationships in the albite autoclass system. So here we have an albite, 100% albite, here we have 100% autoclass, here we have the temperature, and here the experiment was done at 2000 bars. That means 2 kilobars. So, and here above 800 degrees Celsius or something like this, here we have melt, and in this line we have one alkali feldspar, yeah? That was on the triangle which I showed you before, with the continuously line at 900 degrees Celsius and 750 degrees Celsius, yeah? So if you are running then below 680 degrees Celsius and you are coming to this point, then you are forming here once on this side, you are running around here and forming an albite, and then running around here and you are forming an autoclass, yeah? So if we are increasing the pressure to 5 kilobars, then we do not have a one alkali feldspar here, yeah? So we have here our liquid plus sodium feldspar, and here we have the K feldspar. So, and then you are, if you are running here, then you are crystallizing from here to there. So, but below you do not have one alkali feldspar, you are forming automatically two feldspars, yeah? So, and that shows you how pressure and temperature influences or has an influence of the formation of certain minerals, yeah? It's all depending on the pressure, the temperature, and the volatiles. So in these volatiles are water and CO2. It's most of the time a mixture of water and CO2. That you should have in mind as the ES203 student. So next slide. So here we have the same one. How many slides are left? Yeah, we will then continue with this slide when I'm back, yeah? So then we are done for today. And you know what to do for next week then, yeah? Okay, great.